for creating this forum. Thank you to the organizers for creating this forum. It's wonderful, and thank you for inviting me. So today I'll talk about fracture, peridynamic fracture models, and what is important here or relevant here is that non-local interactions across a finite length scale can have global consequences. A well-known example, in addition to peridynamics, a well-known example that's been worked on for a little bit longer include the Cuker Smale model, where flocking emerges from nearest neighbor interactions. Here it's velocities of nearest neighbors as opposed to the displacement of nearest neighbors, but it's seen and in that context. And what is important in this lecture here is to stress that fracture as modeled by a non-local peridynamics, for example, or exclusively really, can be modeled as an emergent phenomenon, as an emergent dynamics. So we'll postulate a dynamical system and fracture will emerge from it. And such emergence is a hallmark of these peridynamic models that were introduced by Stuart Silling in an article that appeared in Journal of Mechanics and Physics of Solids in 2000. Okay, and so to fix ideas, just let me give you a sort of a cartoon of peridynamics. You know what it is. So basically, it's a rule and for a deformation of a solid, and the or displacement of a deformation of a solid. So imagine a material point at X. So that first bar here, U at T at X. Imagine that a material point at X displaces, and U is its displacement, and it changes with time. And what is acting on X, the point X, is a force due to the displacement of a material at point Y. The distinctive feature here is that we look at a neighborhood of points nearby to X. And so H here, H epsilon, is a ball in dimensions 2 or 3 of radius of length scale epsilon. And what we do is we sum the forces of points Y acting on point X, and we sum all these forces for all Y's in the neighborhood of X. And that will give us our net force, and that, by this model, accelerates. That the U double dot is the two time derivatives, rho is the momentum, and so accelerates and gives us force times mass times acceleration. So mass here is the density. The acceleration is the second derivative of U, and it's equal to the force acting on X at X, and that force is the sum total of forces acting on X in the neighborhood of X. So this is the non-locality, and the length scale is epsilon, and so this is very much like Stuart's introductory talk yesterday, where we had some non-locality. Now, the point is that this force is a prescribed force, and it discusses the interaction of nearby points. But such models can have more global features. So now I want to show you a numerical analysis which exhibits this. So we're going to use a peridynamic model similar to this one here, given by 1, with the force we'll say is elastic, but then if it gets too strong, if the strain between, say, points X and Y gets too big, things may break. It could break. So we're going to use that force and that dynamics that I just showed you, and we're going to fill a material with it, with that force, and we're going to impact it with a cylindrical impactor coming down at 32 meters per second. It's going to hit a ligament where here this is air on both sides. Here we're zero displacement boundary conditions, so we're fixing it. Here it's zero traction, okay? And here it's zero traction as well. And so we're going to hit this and impact this material. And the forces and the acceleration are governed by an equation of this kind of form. And we will see what happens. And so what happens is the impactor strikes the sample. These are these are held displaced. These are fixed displacements, so they stay the same. But this thing shifts and cracks. Okay, these are intact here, intact here. This material is intact here, but we have a crack. Okay, and this is a numerical simulation of Nathaniel Trask, Yu, and Michael Parks in their 2019 article in Computer Methods and Computer Methods in Engineering and Computer Methods in Engineering and Applications. And so from that dynamics emerges this fracture, and it's symmetric on both sides. And what they find is that the angle at which that fracture made with the vertical is 68 degrees in agreement with experiment. Now, here, that is an emergent phenomenon because that 68-degree angle was not part of the dynamic formulation. It emerged from the model. And so that's what we mean by a field theory, and it's very, very compelling. So we have an emerging fracture emerging from a simulation. Okay, this is very similar in spirit, at least, to let us say a Cuker Smale and the emergence of flocking due to nearest neighbor interactions. Okay, in this lecture, what we want to do is we want to compare the peridynamic fracture model to other fracture models to see how they relate to each other. Okay, and so what we're going to do is we're going to take the length scale of here it would be the horizon of interaction, and we're going to pass and ask that the horizon becomes smaller and smaller and smaller. So we're going to look at the length scale of vanishing horizon and its effect on the dynamics. And what we will do is we will write down the equations associated with that dynamics, and then using the equations alone and no hypotheses, we'll send the horizon to zero and see what the limit dynamics is. Okay, so that's the idea here. So in order to do that, we have to definitely have our field theory posed on a suitable function space. That suitable function space should allow for fractures, okay, as well as the force. And it's nice because actually the functional analysis is quite simple, and we can pose this really peridynamics as an ordinary differential equation. The time derivatives are the only derivatives here on a Banach space. The right-hand side, the force could be complicated, but in principle, it's an OD on a Banach space. Lipschitz continuous on that Banach space, and we have well-posed formulations for state and bond-based ODEs, notably Etienne Emmerich and Dimitri Pulst posed for a certain type of damage and showed well-posedness. And then Chung and Chao Chen and I don't know his name, but Ms. Tao, journal elasticity, they for a different type of damage model, they show existence. And then more recently, we used the model of Emmerich and Pulst to do some state-based existence. And then there's some other earlier ones showing well-posedness ODE in a Banach space for an unstable bond model. Well, anyway, for this mathematical well-defined theory, then we can compare now in a quantifiable way how the emergent theory given by non-local models converge to other classic fracture models as the non-locality length scale goes to zero. So in this talk, we'll take the small horizon limit of peridynamics, a certain model, and I'm going to explain that model in the next slide. But to summarize and kind of give an overview, in the small horizon limit will demonstrate convergence um, to a limiting model in the limit of vanishing non-locality, which will involve an evolving fracture set. It's shown that we will show that the evolution converges to the wave equation for time-dependent domains. Here, this wave equation for time-dependent fractured domains is the one recently introduced by Dal Maso and Toader in Journal of Differential Equations. So peridynamics, taking the limit, actually makes contact with this notion of time-dependent fracture domains for sharp interface. Well, actually, just time-dependent fracture domains. Period. No. We show along the way we can show that the limit evolution itself has bounded linear elastic fracture mechanics energy, just using the non-local evolution equations and integration by parts and taking limits, we can show that on the crack flanks, this growing crack, we have zero normal traction, which is consistent with our understanding of linear elastic fracture mechanics and what happens on the sides of cracks. And applied math arguments show actually that the crack tip kinetics, that is the rule for how a crack tip should move, is given by linear elastic fracture mechanics, provided that the crack velocity is not too high, because that's where the linear elastic fracture mechanics works. If you go higher than that, you can hit instability, and then your crack can bifurcate. So we'll just look at stable crack growth, and that's where linear elastic fracture mechanics applies. And we see that peridynamics actually, as the horizon goes to zero, approaches, actually has inside it already in its constitutive laws, the kinetic relations for linear elastic fracture mechanics, which is somewhat surprising, but they just pop out. So let me just review very quickly, the non-local model as we're going to use it. We have a ball, which we call h of epsilon. Epsilon is the diameter of the ball. So it's of length epsilon, or the radius of the ball, it's of length epsilon. The ball is is centered at the point X, it has radius epsilon, and then Y's other points that are within the ball are denoted by Y. And then basically interaction between the points Y and X only happen inside this ball. If the point Y is outside, it doesn't exert any force on the point X. Otherwise, if it's inside the ball, it will exert a force on X. Now I'll explain what those forces could be. Well, in this particular model, the currency is a strain, okay? And so to understand what the strain is, we take the displacement at X, we'll call it U at X, and I've suppressed the time variable here. And so yes, the displacement depends on time as well, but I suppress it and just say U at X. And the strain between 2 points X and Y is simply denoted by S, strain, is the difference in the displacements divided by the distance between the 2 points resolved along the direction E, which is the direction of Y pointing towards X. Okay, so that's this tensile strain in the direction E. And so then what we're going to do is we're going to have a force potential that's going to exist. And basically the abscissa here, R, is the strain, and the ordinate here is the force, or is the force potential, okay? And this is a particular simple potential, and we could take something that looks more Leonard Jones-like as well, but I fix ideas and look at this potential. And then I just noticed here that the total, this is the force that I just showed you. It depends upon the strain this way. And this is the distance between Y and X multiplied by the strain. And it's divided by 1 over epsilon, okay? And you're going to see in a minute why this looks this way, okay? It's set up. So this is, you could say, a constitutive law. This is the constitutive law of the model. And if I take the derivative of the force potential, I'll get my force acting between 2 points x and y increases initially with strain, and then at some critical value, it starts to soften, and then it softens to 0. Okay, and likewise under compression. Now, we could make this such that this doesn't go to here, it could go way down and resist compression a lot more than it does strain. But to fix ideas, I've left it like this. So then our force on our at x due to a deformation u at time t is simply the sum of all of the forces summed over all y's for y inside the ball. And then let us say centered at x, and let us also say that x has to be in some domain. So we're going to look at a finite sized body. The body itself will be called D. It could be in 2 or 3 dimensions. It'll be connected. It's finite size. You know, for right now, we can assume that it's smooth on the boundary, but it doesn't have to be convex. We can make it more bizarre if we want to, but just let's take a nice smooth body. And so as long as x is in the body, then we have some force. As we get close to D, then our force will be, it'll be affected by the fact that D is there, but it should be. Okay. So the dynamics on the domain, here's the domain. The dynamics is again, acceleration at the point x at time t multiplied by the density. Here we'll assume the density is the same for every x in the domain, is equal to the peridynamic force, the non-local force, plus a body force. Okay, our body force here is local and at each x, at each point in the domain, and it may change it with time, but it's prescribed. So the body force is prescribed. We're considering basically a Neumann problem here. So that's why the boundary conditions are not prescribed. Just to note, one note is that rigid rotations, we do not consider rigid rotations. So we mod those out. The reason is because this strain for rigid rotation, the strain, it lays in the kernel of the strain. So we mod those out. So it's a pure Neumann problem. So we're going to, and so basically we could think of the layer of body force along the boundary of it. Now, what I wanted to show you is what is called a failure zone. So we don't have a crack in a peridynamic model, but what we can do is we can prescribe a failure zone. And so to fix ideas, well, suppose we have a failure zone center line. So there's some line in which there's going to be failure. And the idea is that you have a point X in this figure here. And for Y's above this failure zone center line, Y and X do not interact. That is it's on the phase, so it's on the softening part of the, it's already softened to 0, okay? So it's softened to 0 for any pair of points, X and Y, that lie across the failure zone, okay? And inside this horizon. So that's what we call a failure zone. The failure zone is the, if you will, the union of all centroids of these balls such that bonds on the other side of this line are, the force between 2 points is 0. Okay, and just to give you an idea, if we do a numerical simulation of this problem that I just showed you, we get this is our numerical simulation, and the red shows the failure zone. Okay, the blue shows the intact material. The red shows that very zone I was just talking about. And we can draw an artist's conception of the failure zone. Here I called it FZ for a given diameter. And here's the failure zone center line right there. And then we have a epsilon above and epsilon below. And basically this is the tip of the failure zone at some time. And what we have here is we have intact material in the clear area. And in this is the softening zone. So basically on either side of this center line, the bonds are now softening. They're not failed yet, but they're softening. Over here, if we're in front, no, bonds aren't softening yet. We're in the elastic phase. But as soon as the crack moves, so if we imagine you wait a minute and the crack moves and now you're here, well, now you're softening. And once you've crossed over here, you've failed. And so this is the failure zone. And this is sort of a smeared out, if you will, crack. Okay, it actually has dimensions, okay, of epsilon below and above epsilon above the crack. Now, the question is, well, in order to do all that, you had to exert some work, or you know, it required to soften the bonds. So can we do some back of the envelope calculation to see how much energy it required to make per unit length of this center line to soften bonds on this side, on either side of the this failure zone? How much work is involved given the equations of motion, because that's all we can use to calculate? Well, we can define a fracture toughness, which has been defined by many authors, and we follow that, where you have a point here, X, and you have another point here, Y. They lie across the failure zone. And the idea is how much work do I have to expend in order to fail a bond between here and here? And then actually I want to add up all the bonds that are going to fail as I take X epsilon away from this centered line here. Okay, so we want to add up all the bonds. Well, one thing I wanted to say is that now that scaling, remember I divided by epsilon and I did some tricky stuff and when I defined the potential, and the idea is that is because for this model, the fracture toughness is the same for all choices of horizon. Okay, so we're working with a family of models with the same fracture toughness, and it will turn out through direct calculation that the fracture toughness is independent of epsilon. Okay, what this does is this aspect implies the smaller the horizon, the smaller the transverse dimension of the failure zone. This means that the failure zone flattens out and becomes a crack in the limit of 0 epsilon. In fact, Grunwald's inequality applied to the equations of motion show that the volume of failure zone is of order epsilon. So localization actually is hardwired into this model without doing anything. Okay, just a back of the envelope Grunwald inequality will show you this. Okay, now we go to the formula. So we calculate the amount of work or power required to fail all these bonds in this cap, and then run X here. This X point starts here at the failure zone and run it to epsilon and find out and integrate and find out the power required. Now, this was done by for a different model, but it's always the same no matter what peridynamic model you did. Stewart and Ibrahim Ascari did it originally. That's where I found it first. And a beautiful, beautiful calculation. And you can apply our model here, and you do, and boom, you get that the fracture toughness you see here directly from this formula does not depend on epsilon. It's the same for all epsilons, and hence the scaling here. Okay, what about the last thing is okay, what about elastic coefficients? Can we relate elastic coefficients when the bonds are in the linear regime to classic elastic coefficients? The answer is yes. All we need to do is expand the peridynamic energy in a Taylor series, and we immediately get that to leading order the peridynamic energy. That's what I call this where here we're taking the integral around the horizon and everywhere. And what we do is here we look for a linear strain here, and we resolve it along direction X, epsilon, sum over all Y's in the neighborhood. We get a limiting the peridynamic energy looks to first order toward leading order like linear elasticity, where the Lemay moduli are given here. The shear moduli is given by a formula in 3 dimensions, and the Lemay moduli is also given by a formula. They're the same here because we were looking at bond-based peridynamics, but it's enough to just start with this. And also we can do it in 2 dimensions. Now, what do we want to do? Well, for our model then, we want to approach a local fracture model in the limit of vanishing non-locality. So we can consider a sequence of solutions associated with a sequence of horizons and follow their dynamics. And we get convergence of this non-local dynamics. Provided we have the same initial data, then the evolutions converge in mean square uniformly over a time interval to a limit evolution. And this limiting evolution actually has bounded linear elastic fracture mechanics energy, okay? And this is true actually no matter what the crack set happens to be. This is what you get. And you get that this is the elastic part of the energy, and this is the surface energy here. This is the fracture toughness. Notice here, this is the same fracture toughness that we calculated using the formula. This inequality here comes from Grunwald's inequality. We have to pass to a limit. We do that using gamma limits, and heuristically, this area is given by Crofton's formula. It actually follows from the peridynamic potential in the limit, and because we could use Crofton's formula, and it's a very nice calculation. Okay, away from the failure zone, then we can say, hey, in any quiescent region where fracture hasn't occurred, we pass the limit as epsilon goes to 0. We get a limit evolution, and the limit evolution actually evolves elastodynamically according to the Navier-Lemaitre equations, as long as no fracture hits through there, passes through there, and we're given that the stress tensor is given by the usual stress tensor for linear elasticity, where these are the coefficients I computed just a second ago. Okay, now the question is, well, wait a minute, let's suppose now the crack does go through. We're not going to look at quiescent region anymore. We're going to actually look at just regions that contain cracks and intact material. And so we apply our traction loading conditions. We'll notch the specimen, and we'll grow a crack from the notch to the right. Since we're pulling symmetrically, the crack will stay along the x1 equals 0 axis. I mean, the x2 equals 0 axis. Vertical axis will be x2, horizontal x1. And if we do it numerically, we see it right away. When we pull, we get a crack propagating from the notch, and it's moving inward, moving to the right. Well, what happens? In the limit of vanishing horizon, what we get is as epsilon goes to 0, we get an epsilon equals 0 solution. We get a balance of linear momentum described by the linear elastic wave equation in a time-dependent domain, and 0 traction on the crack lips. Here, dt is the time-dependent domain. The boundary of dt is the sides, the notch, the sides and the top and the bottom, as well as this new piece of boundary that's evolving with time. That's the crack. Okay, this new piece of boundary is evolving with time, growing, and outside it, we solve the elastic equations, and basically on the crack faces, if you take the trace coming from below, you get 0 normal traction. If you take the trace coming from above, you get 0 normal traction. And in fact, we can actually say how we are converging and in what topology. Remember, I did say we have to specify the function space and the whole thing. Here, this dot refers to the fact we mod out rigid rotations. That's all that dot is for. And actually, we get convergence of a kind. Okay, what are the properties? Again, the properties of the limit deformation is, well, for a crack, that's gamma t. That's going to be on the x2 equals 0 axis, and it's for coordinates between that should be L0 of t, not L0. I mean L0 of 0 when t equals 0. The left inner point in this interval is L of 0 at 0. The right end point is L0 at t. Okay, and what we find is that u is actually a special function of bounded deformation. Okay, such that the regular part of the radon measure which is the symmetrized strain tensor is square integrable over d. And the crack, the jump set, is contained inside the fracture set. Okay, and in particular, it's actually given by SBD of D. Yeah, exactly this. That's what we call this. This is the definition.
Rob, 2
Yeah.
minutes.
Okay, perfect. So the great thing is that we have this wave equation, solving the wave equation on this moving domain, and U is actually more regular. It's actually an H1 of dt. It's zero traction on the crack lips. And now the last question we say is well, what's going on the tip of the crack? Can we, just from these motions here, the dynamics, deduce what's happening on the tip of the crack? And the answer is yes, we can. This is done in the recent paper, but in International Journal of Fracture. And what we do is we take a domain that contains the tip of the crack here. This is the actual crack, the fat crack. We contain it, and we contain it. We actually, the whole domain, we look at the energy coming in, the energy going out, and ask what's happening to the internal energy. This is the kinetic energy density. This is the stress power flowing into the domain, or the stress power density. The time change of the internal energy is equal to I minus E, where I is the flux of stress power in, kinetic energy in, and E is the flux of the elastic energy into the domain. We pass to the limit. We take epsilon goes to 0 here in this identity. We pass to the limit, and we get to leading order that the stress power flux is equal to exactly the power required to make interface per unit length. And we more generally get this identity, which says that the change of internal energy inside to leading order, there is the stress intensity factor sitting there. Here is the velocity of the crack. Here is the energy release rate. And when we have power balance, that is the time rate of change is 0 here. That is this. We get back the famous celebrated relation given by Rodney Clifton, Ben Frund, and John Willis that says that the fracture toughness is balanced by the elastic energy flowing in, characterized here by the energy, by the fracture toughness. So with that, I conclude. All I can say, I'll say one thing. We could do a numerical experiment. Here it is. Here's a growing crack. In this region here, we have basically constant crack growth. We're pulling on the upper and lower parts of the domain. We get our growing crack here. We start here, we go faster, we top out, we're constant speed crack. And the great thing is we can measure, and this last slide, this is the last slide, we can measure the orange and green. The green is the power, the stress power, and the green is, and the red is the energy release rate. And we have it 1-to-1, they match, they're on top of each other. And this is in a numerical simulation. So we see this corroborated numerically. I've listed the following publications in which the results have been proved. Publications listing a priori convergence analysis is here. I didn't talk about that today. And in conclusions, non-local interactions have global consequences, and fracture is an emergent phenomena. And thank you very much.